Welcome to Dialogue. Science. For centuries, it's been our ultimate truth-seeking mechanism. It's the bedrock we build everything on: modern policies, medicines, our whole understanding of the universe, really.
No, it is. And it's all fundamentally built on one simple, beautiful idea.
Self-correction.
Exactly. Self-correction. If a finding is really true, if it reflects reality, you have to be able to prove it again. It has to be replicable.
Right, it has to stand up to a skeptical colleague running the exact same steps.
And that principle, that idea of repeatability, that's the silent contract science makes with all of us. It's what turns a clever observation into a fact we can actually build on.
But the whole reason we're doing this deep dive is to talk about something.
Yeah.
Well, something unsettling.
Yes, the structural instability that's facing the entire research world, the replication crisis, what happens when those building blocks of knowledge, the studies cited thousands of times.
The ones that entire careers are built on.
Those ones, what happens when they fail spectacularly to reproduce when someone tries to run the experiment again?
It's more than just unsettling. It's a real crisis of confidence. And our mission here is to look right into those cracks, within science itself. We want to examine the internal pressures, the flaws in the methods that have created this instability.
This isn't about, say, public misunderstanding or external actors trying to manipulate things.
No, that's a downstream effect for sure. This is about systemic failures. It's about how the very engine of knowledge has, ironically, started producing fragile knowledge.
So we have to look at the internal architecture, the incentives, the subtle shifts in how science is done that have led us to this point. I mean, why are entire field, we're talking everything from psychology to cancer research, now having to reevaluate their core foundations?
That's the key question we want you, the listener, to keep in mind throughout this conversation. Why are we seeing this profound instability in what we thought were pillars of knowledge? And, maybe more importantly, what does this fragility mean for how you evaluate information every single day?
Let's start by defining the scale of the problem.
Okay, so the foundation of trust in science, it rests entirely on that ability to verify. You read a paper in a good journal, you trust the conclusions, and you just assume that if you follow the exact same steps,
With the same materials, the same analysis.
you'd get the same result. That's the gold standard. It's the ideal.
And when that ideal fails, and fails consistently, the consequences are immediate and they're profound. They just cascade through the whole system.
How so?
Well, when a cornerstone study fails to replicate that critical line separating reliable, tested knowledge from, a fragile assumption, it gets dangerously thin.
So we stop building on a stable foundation.
We start building on sand. And the momentum of an entire field can just grind to a halt because researchers are spending time and money chasing findings that were basically statistical ghosts.
And we're not talking about tiny disagreements over a decimal point here, are we?
Not at all. We're talking about findings that either vanish completely or the effect size, the strength of the finding, is so drastically reduced it becomes meaningless in the real world.
Think about the economic cost. Research is incredibly expensive.
Staggering. The amount of money and time that researchers, institutions, governments waste trying to build the next step on a claim that was never real in the first place, it's millions, sometimes billions of dollars.
And that loss of certainty, it must paralyze progress.
It does. Take drug discovery. Studies have shown that even in preclinical cancer research, findings published in the top journals, they often fail to replicate inside pharmaceutical companies trying to validate them for human trials.
So the very first step, the knowledge coming from academia, is often faulty.
Frequently, it creates massive sunk costs before a drug even gets close to a patient.
And what about the human cost for the researchers themselves? I mean, a graduate student might base their entire PhD on a core finding.
And then 2 years in, that finding fails a big replication test. Their whole theoretical framework just collapses. It's devastating.
It must force a certain humility, which I guess is good.
It is, but it also creates immense career risk and slows down the whole process of training new scientists.
And then there's the public trust angle.
Which is arguably the most corrosive consequence, especially today. If the experts themselves, working inside peer-reviewed systems, can't agree on the basic facts because the facts aren't reproducible.
How can you expect the public to maintain any faith in the process?
You can't. This instability is just a gift to people who want to undermine evidence-based policy or spread misinformation.
So when we trace this back, it's not random error. It's a combination of poor methodological shortcuts, the how, and a research system with misaligned incentives, the why.
Exactly. And to really get it, we have to look under the hood at the technical side first. the tools researchers use every day, especially statistics, and how these tools for precision have been, well, misused to create these unstable results.
Okay, let's get into that statistical nitty-gritty. This is where tools meant to find a signal in the noise are instead used to create noise that looks like a signal.
And the first crack in that foundation, the most common one, is a flawed reliance on something called null hypothesis significance testing, or NHST.
Right. And at the center of that is the p-value, that infamous number.
The p-value. For decades, scientific communication has been dominated by it. That threshold of 0.05. It's treated like this ultimate gatekeeper. If your p-value is below 0.05, you have a real finding. If it's above, you have nothing.
But it's so widely misunderstood. People think it's the probability that your result is just due to random chance.
Which is not what it is. It's actually the probability of seeing data at least as extreme as what you found, assuming the null hypothesis, the idea of no effect, is perfectly true.
So in simpler terms,
It's a measure of how surprising your data is if your intervention did absolutely nothing at all. A low p-value just means your data is very surprising under that assumption of no effect.
which leads the researcher to say, okay, I reject the null hypothesis, I found something.
Exactly. But the key confusion, the one that leads to non-replication, is that a low p-value tells you nothing about whether your hypothesis is actually true or how important your finding is. It just tells you something about the data,
And that encourages this binary yes or no thinking.
which is terrible for science. It pushes researchers to fish for that significant result, which leads to findings that look solid but are really just statistical artifacts. We call it a type I error, a false positive.
Claiming an effect exists when, in reality, it doesn't.
And those are the studies that fail replication so spectacularly.
Okay, so if statistical misuse is one key vulnerability, the second major factor seems to be just a weak study design,
Yeah.
specifically sample size.
The problem of small sample sizes is everywhere, especially in fields where it's expensive or hard to get participants, like neuroscience or early drug trials.
And the incentive is pretty obvious, right? Time and money.
Absolutely. If you're fighting for a limited grant, a smaller sample means you finish faster, you publish sooner, and you get the next round of funding.
So it's efficiency, but at the cost of truth. Let's get technical, though. What's the actual statistical consequence of using a small sample? Why does a result from, say, 20 people disappear when you try it with 200?
The key concept is statistical power. Power is the probability that your study will correctly detect an effect if that effect is real.
And small samples mean low power.
Inherently, a low-powered study is like trying to weigh a truck with a kitchen scale. The instrument just isn't sensitive enough to reliably measure what you're looking for.
So when a low-powered study does get a significant result, what's happening?
It's often just random chance, statistical luck, and small samples drastically increase the likelihood of two bad things happening. First, that false positive we just talked about.
Okay, and the second?
They wildly exaggerate the effect size. If a treatment truly has a small, modest effect in the real world, maybe it helps 5% of people, a small study that happens to find a significant result might report that effect as being 30% or 50%.
So the initial finding is massively inflated.
Hugely. Then, when a bigger, high-powered study is done, that finding either disappears entirely or it settles down to its actual, modest, real-world value.
Which is often too small to justify the original breakthrough headline.
Exactly. And this is where the system's bad incentives and the flawed methods really start to feed each other.
Because journals love sensationalism.
They jump on these early small sample findings because they report these huge exaggerated effects. They get labeled as major breakthroughs.
And then an entire body of literature gets built on top of this fragile claim that was basically guaranteed to fail a large-scale replication.
And that toxic mix of statistical vulnerability and low power opens the door to the more deliberate shortcuts. P-hacking and O-sharking.
P-hacking. That's the term you hear all the time. It's basically massaging the data till it tells you what you want to hear.
That's a good way to put it. It involves making choices in how you analyze the data after you've seen the initial results, specifically to get that p-value below 0.05.
Can you give an example?
Sure. Imagine a researcher runs an analysis and gets a p-value of 0.07. Close, but not significant. So they might decide, well, let's exclude these two outliers. Or they might try adding a new control variable they didn't plan for. Or maybe they only look at participants who took the survey in the morning.
They're running the analysis 20 different ways until one of them works. The garden of forking paths.
Precisely. They're violating the core rule, which is that you plan your analysis before you see the data. The data is supposed to test the hypothesis, not the other way around.
So the finding they publish is totally specific to that data set and that one weird analysis they chose. It's guaranteed not to replicate.
And its cousin, harking hypothesizing after the results are known, is just a masterclass in storytelling.
Right. So this is where you find a surprising result by chance and then pretend you meant to look for it all along.
That's it. You run the data, and you see some totally unexpected correlation. Maybe people who listen to classical music did slightly better on a math test. That wasn't your original hypothesis at all.
Your hypothesis was about sleep.
Right. But you see this positive result, and so you invent a sophisticated theory after the fact. We hypothesize that classical music activates frontal lobe pattern recognition centers, and you present that in the paper as if it was your guiding idea from day one.
So the final paper reads perfectly. The narrative is clean. The conclusion seems to flow logically from the intro.
But the whole thing was built backwards to fit a statistically lucky result.
And both of these practices, p-hacking and hark-harking, they just distort the entire scientific process.
They prioritize getting published over finding the truth. They create research that looks solid on the surface but is built on a foundation of sand.
Okay, that is a remarkably clear picture of the how. So now we have to get to the why. If researchers know this is bad practice, why does the system push them to do it?
That takes us squarely into the systemic incentives, and it starts with publication bias.
The preference for positive results.
An overwhelming preference for excitement. Journals, especially the top-tier ones, want new discoveries, groundbreaking effects, dramatic conclusions. That's what gets them citations and prestige.
It's a marketplace, and novelty is the currency. They want the finding that gets a press release, not the one that just confirms last year's work.
Precisely. And this creates a huge, invisible flaw in the scientific record. Studies that find nothing, what we call null results, are routinely suppressed.
They just end up in a filing cabinet somewhere, the file drawer problem.
Exactly. And the consequence of that is devastating for our collective knowledge. It means the scientific literature, the thing we rely on for policy and medicine and everything else, becomes dramatically skewed toward positive, often dramatic findings.
It creates a false sense of consensus.
It does. Imagine 50 research teams are studying a new learning technique. 40 of them find it has no effect. Their studies are boring, they never get published.
But 10 of them, maybe because of a small sample or a bit of p-hacking, find a positive result.
And only those 10 get published. So if you're a reviewer looking at the literature, it looks like there's overwhelming evidence that this technique works.
When in reality, 80% of the evidence says it doesn't, but that evidence is invisible.
Buried in the file drawer. So the literature is operating under this massive positive bias, and the complex, often null reality just isn't represented.
And this feeds directly into the misaligned incentives. What are researchers actually rewarded for?
Almost exclusively for quantity, novelty, and speed. Not for quality, not for rigor, and definitely not for reproducibility.
Success is measured by how many papers you publish in prestigious journals.
Right. That's what gets you tenure, that's what attracts students, and most importantly, that's what gets you the big government grants to keep your lab running.
So you're saying a junior researcher trying to get tenure is better off rushing out 3 new, fragile, but novel claims.
Then spending 5 years painstakingly replicating 20 old findings to see if they're actually true. That careful work is seen as less productive and less high impact.
The system literally rewards the flashy claim over the solid foundation.
It is a massive pressure. It's an incentive trap where the rational thing for an individual researcher to do to keep their career alive is fundamentally at odds with the collective goal of finding objective truth.
And it's important to say this isn't about malicious people.
Not at all. These are human beings acting rationally in a hyper-competitive system. If the system demands rapid, dramatic, positive results to get the next grant, then that is what the system will produce.
Which brings us to the ultimate paradox here. The devaluation of replication studies themselves.
It's the core of the issue. Replication is quality control. It's the essential check on a claim. And yet, it's treated as a waste of time and money.
Why bother confirming something when you could be discovering something new?
From a career perspective, it's a dead end. Journals rarely want to publish successful replications because they're not new. and they're often hesitant to publish failed replications because it can look like a personal attack on the original author.
And I imagine grant agencies aren't lining up to fund them either.
Not at all. They'd rather fund the promise of a new discovery than the boring work of confirming an old one. So a researcher who dedicates their time to replication is actively hurting their own career metrics.
The system actively punishes the one behavior that is most vital for scientific health.
And the result is this huge pile of claims that never get that necessary independent check. We end up with a body of knowledge that we assume is solid, but when you actually scratch the surface, it often just crumbles.
We're prioritizing laying new bricks over checking if the foundation is sound.
That's a perfect analogy.
Okay, so if the system is pushing for speed and novelty, and researchers are using these fragile methods, where are the cracks most visible? Which fields are struggling the most?
That's a great question. Because certain fields, just by their nature, have a harder time with this, and it amplifies the problem.
Let's start with psychology. They were sort of the first to really confront this crisis publicly, right?
They were. Psychology, especially social psychology, has been a central battleground. The struggles there often come from small samples and the immense difficulty of measuring complex human behaviors.
You're talking about things like social priming, right? Where a subtle cue is supposed to change behavior.
Exactly. You expose someone to words related to old age, and then you measure if they walk more slowly down the hallway. These effects are notoriously dependent on the specific context.
The exact phrasing, the time of day, the culture of the participants.
All of it. It makes them incredibly hard to standardize and reproduce. And when large-scale projects tried to rerun these classic studies, they found a huge drop-off.
The effects just vanished.
They either vanished or the effect sizes shrank so much they became scientifically trivial. The famous ego depletion theory, for example, the idea that willpower is a limited resource, that's been a cornerstone of psychology for years. But large-scale pre-registered replications have found null or ambiguous results.
So the original findings were likely just a product of low power and publication bias.
That's the running theory. It was just a neat story that fit the data by chance.
Okay, let's move to biomedicine. Here the stakes feel so much higher. We're talking about life and death.
Absolutely. Biomedicine has what's often called the valley of death, the huge gap between a promising result in a lab and a successful human clinical trial. And the problem is often unreliable biomarkers.
These are the indicators used to predict or track a disease.
Yes, or measure how a patient responds to treatment. You'll see high-profile papers announcing a potential new biomarker, but it's usually based on early animal studies or work in cell cultures.
And why don't those translate to humans?
Because the early research often lacks basic rigor. The animal studies use genetically identical mice in perfectly controlled lab environments. That doesn't account for human genetic diversity, diet, lifestyle, other medications.
The messiness of real life.
The messiness of real life. And the statistical analysis in those early papers can be just as prone to p-hacking and small sample issues as in psychology. It leads to these overpromised drug targets that waste immense resources when they inevitably fail in humans.
And finally, a field that affects every single person listening, nutrition science. It feels like the advice is constantly changing.
Nutrition science struggles because its main tool is often observational studies that rely on people remembering what they ate.
The food frequency questionnaire.
Right. Asking someone to reliably recall what they ate over the last year is, well, it's a very noisy measurement.
And you're trying to isolate one thing, like saturated fat, from a whole lifestyle.
An incredibly complex lifestyle. Diet, exercise, genetics, stress, sleep, they're all tangled together. It's almost impossible to control for all those confounding factors.
So most of the findings are just correlation, not causation.
Exactly. People who eat more organic food also tend to be wealthier and have better health care. Is it the food or is it the wealth? It's nearly impossible to say.
Which leads to the endless cycle of contradictory headlines. 1 year coffee is a miracle cure, the next, it's poison.
The inherent difficulty of this subject, combined with the pressure for headline-grabbing advice, just ensures a high rate of replication failure.
So we have these academic issues, but they don't stay in the lab. What are the real stakes for the rest of us when these studies fail?
Well, it hits policy, medicine, and public action directly. When studies in economics or public health fail, you get unstable public policies. Governments spend billions on programs for education, poverty, the environment, based on research that turns out to be fragile.
So the policy fails, money is wasted, and people lose faith in the government's ability to solve problems.
Exactly. And in medicine, unreliable research leads to misleading treatments. Doctors rely on journals to stay up to date. If those journals are publishing non-replicable claims, patients can be pushed toward expensive, ineffective treatments.
Or even worse, diverted from things that actually work.
And this all feeds the most dangerous consequence, the erosion of public trust and expertise itself. Every time a major finding is shown to be false, it chips away at faith in science as an objective source of information.
It fuels skepticism and polarization.
It does. It creates this dangerous sense that science is just another biased narrative, that it all depends on who funded the research.
It all comes back to the human reality. Science is done by people, people under pressure, with budgets, with careers to build.
And they are working in a system where the incentives don't always align with the slow, careful, tedious pursuit of objective truth. Recognizing that systemic human pressure is the first step toward fixing it.
We've painted a pretty bleak picture of instability, and it can feel overwhelming. But I think the most hopeful part of this whole story is that the scientific community itself is the one leading the charge to fix it.
Absolutely. This crisis is, at its heart, a self-aware scientific movement. It is the ultimate act of self-correction.
The identification of the problem has spurred this profound push for more rigor and transparency.
We're seeing specific, actionable solutions being put in place to counteract those bad incentives we talked about.
Let's look at some of those, starting with the countermeasure to p-hacking and arcing. Pre-registration.
Pre-registration is a simple but really powerful idea. Researchers publicly state their hypothesis, their sample size, their methods, and their full analysis plan before they collect any data.
They post it to a public repository, so everything is on record.
Yes, and this immediately solves p-hacking because you're locked into your primary analysis. If you do some exploratory analysis later, you have to label it as such. You can't pass it off as your original plan.
And it solves haching because the hypothesis is registered before you even know the results.
It restores that critical distinction between testing a hypothesis and just finding patterns in data. It adds a huge amount of credibility to the findings.
Okay, what about the publication bias problem? The file drawer.
For that, we have something called registered reports. This is arguably the most effective solution.
How does that work?
With registered reports, journals review the study's methodology and analysis plan before the data is collected.
So they're judging the quality of the question and the rigor of the method, not the result.
Exactly. If the methodology is sound, the journal grants an in-principle acceptance. That means they will publish the paper regardless of the outcome, whether the result is positive or null.
So that completely changes the incentive for the researcher.
It flips it on its head. You're no longer rewarded for getting a flashy result. You're rewarded for designing a rigorous, high-quality experiment.
And this should, over time, fill the literature with all those missing null results.
That's the goal. To give us a much more accurate picture of reality, major journals are starting to adopt this format, and it's a huge step forward.
We're also seeing a massive push for open science in general.
Yes, which is all about transparency. Researchers are now expected to share their raw data, their statistical code, their lab materials.
So if another lab tries to replicate a study and fails, they can go back to the original data and code and figure out why.
Right. Was it a mistake in the original paper? A subtle difference in method? Or was the original finding just not robust? It makes the whole process accountable.
This whole movement, this willingness to admit to foundational flaws and fix them, that really is what defines the power of science.
It is. And it brings the whole discussion back to you, the listener, and how you process information. Understanding this crisis forces us to ask much deeper questions about what we think we know.
You have to think critically about the health advice you read, the business theories you follow. How much of what we accept as fact is built on one of these low-powered, small sample studies that was never really tested?
We have to move beyond just accepting things because they come from a source of authority. We have to develop a critical lens that understands the system rewards speed over reliability.
The takeaway here isn't to distrust all of science. It's the opposite.
Exactly. It's about learning to tell the difference between rigorous, replicable science and a fragile, novel claim that hasn't been tested. The best protection against misinformation is to learn to think scientifically.
Which means asking the right questions.
Was this study pre-registered? Was the sample size big enough? Was the data shared? Has anyone else, an independent lab, gotten the same result?
Understanding the mechanics of this crisis gives you the tools to look past the sensational headline and see the real weight of the evidence.
That clarity, knowing what to ask when you see a new study, is the essential skill for navigating the world today.
That's an incredibly powerful way to frame it.
So as you move forward, just consider this. The next time you see a big new findings splashed across the media, a breakthrough diet, a new psychological trick, a startling economic trend, ask yourself if it passes the basic tests we've just discussed.
Applying that critical framework is your first line of defense.
It's the best defense against fragile knowledge, and it's the ultimate way to honor the true scientific process.
If you enjoyed this conversation, please like, subscribe, and share this video. Also, let us know in the comments what really stood out to you in this conversation and if there's any related topic or new topic that you would like covered in a future video.